In this episode, we will discuss two sets of basis vectors in Euclidean space. The first of these bases is called the tangent basis, and the basis vectors EA, with A as a subindex, is defined as being equal to the partial derivative of the position vector with respect to the coordinate chi-a. If we want to get a geometrical interpretation of this, we can look at the coordinate line for the coordinate chi-a. This is the curve in Euclidean space such that all other coordinates are kept constant while only the coordinate chi-a changes. Two nearby points on the coordinate line will differ by a small difference vector dx, and this vector is going to be tangent to the coordinate line. If we take a different coordinate line, drawing here in green, we will get a different tangent vector. So these are correspondingly coordinate lines for chi1 and chi2. And therefore the tangent vectors are E1 and E2. And it should be noted that these vectors are independent of the choice of origin O. Since the tangent basis vectors are linearly independent, we can express any vector in terms of this basis as V equal to the components VA times the basis vectors EA. The vector components defined in this way are called the contravariant components of the vector V. The second basis that we will discuss is the so-called dual basis, and we define the dual basis vectors E with a superindex A as the gradient of the coordinate function chi-a. Geometrically, this means that if we take the coordinate surface, which is defined as keeping a particular coordinate constant as opposed to the coordinate lines where we only change that particular coordinate, then the gradient of the coordinate functions are going to be normal to this coordinate surface. If we take the coordinate surfaces of a different coordinate, say chi2 constant, then we get a different dual basis vector. In particular, if we look at the crossing of two of the coordinate surfaces, then at that point we have a set of dual basis vectors E superindex 1 and E superindex 2. Any vector V can also be expressed in terms of the dual basis. In this case, we write V equal to V subindex A multiplied by the dual basis vectors EA. The components V subindex A defined in this way are called the covariant components of the vector V. Note that in general, the bases defined this way are going to depend on the point in our Euclidean space. So E1 at a particular point is generally going to be different from E1 at a different point. In general, the tangent and dual bases are not going to be orthogonal nor normalized. In other words, the basis vectors are generally not going to be of length 1, nor are they going to be orthogonal to each other. However, the bases are constructed in such a way that if we take the inner product between one of the tangent basis vectors and one of the dual basis vectors, let's say EA times EB, then this is equal to the derivative of the position vector with respect to the coordinate chi-a, inner product with the gradient of the coordinate function chi-b. Using the chain rule for partial derivatives, this is equal to the partial derivative of the coordinate chi-b with respect to the coordinate chi-a. Since the coordinate functions are independent, this is equal to 1 if a is equal to b and 0 otherwise. And this partial derivative is therefore equal to the Kronecker delta BA.